Okay, where we left off was the idea of unit vectors. This is kind of a new concept which can actually make things a little bit easier in some cases. A unit vector, first of all, has a symbol which is just the symbol of the vector, only instead of being topped by an arrow, it's topped by a circumflex. I'm not sure what it's called in English. That's what they call it when they use it in French, anyway. Circumflex. I guess in English we often call it a hat. What it means is just a little hat over the symbol. And U, I'm using U as the symbol for unit vector here. U with a little hat over it is the symbol for a unit vector. The magnitude of a unit vector is always 1 unit, as the name implies. Whatever the unit happens to be. Okay. And you can specify units for the unit vector, but the value of the magnitude of the unit vector is always 1. So the absolute value is the absolute value of the unit vector is the magnitude, which is 1. And it's very actually convenient when you're adding multiple vectors in one dimension. The it also specifies direction. Let me get this there. So, for example, going back to our trip from Buffalo to Rochester, if vector AB has a value of 60 miles east, you can designate a unit vector for that. And we'll just call it U, but you could call it something else if you wanted to. And it would point east. And so you could also write vector DAB B as 60 miles times the unit vector. In this system, the direction west would be negative U. That is the negative of the unit vector. So if you make the return trip from Rochester to Buffalo, traveling 60 miles west, that would be equivalent to negative 60 miles times the unit vector. So that would be, for the return trip. There's an example in the book that we can go over about a ladybug crawling down a, well, I call it a meter stick, only it's apparently 2 meters long. So a ladybug on a 2-meter stick. Okay, we have a 2-meter measuring stick. Leaning on a wall. And the 200 centimeter end, because remember 200 centimeters is 2 meters. So the maximum numbered end of the stick is on the floor. And that means that the 0 meter end is against the wall. This right away kind of turns things upside down from the way we're used to numbering things in Cartesian coordinates anyway. We usually think of greater numbers as being on top and smaller numbers being on the bottom. You know, with, say, on the y-axis, 0 is at the bottom, and in this case, 200 would be at the top. This is just the reverse. So that's going to be a complicating factor. And so the bug lands on the 100 centimeter mark. And I'm going to say it meanders. The book says walks, but bugs don't really walk. They kind of meander. And so I'm going to say it meanders randomly along the stick. And it goes 15 centimeters towards the floor. So what we've got here is a wall and a floor. And the 2 meter stick is laying at an angle, kind of like that, with 0 centimeters there, 200 centimeters there, 100 centimeters about in the middle. And because of the direction that the numbers go, it's probably more convenient for us to define the positive direction as being from 0 towards 200, even though that's downward, which we're not used to. It does at least comport with the numbers. Okay, so actually, when I left off here, the bug was walking 15 centimeters toward the floor. The bug probably traces out, a meandering path as it goes along the stick. But as we saw with our various trips from Buffalo to Rochester by various routes, what really matters here is the displacement. That's what we're going to be asked about, because that is the vector quantity that's associated with distance. And as long as we're looking at displacement, it doesn't matter if the bug takes a meandering path or if it goes there in a straight line. The displacement's going to be the same either way. So the bug was walking 15 centimeters toward the floor. And then the book says 15 centimeters toward the wall, which I think is potentially confusing, because this is the wall here, and this is the floor. And the book says the bug basically goes 15 centimeters. No, wait a minute. It was 56 centimeters. 56 centimeters toward the wall. Well, to me, that the wall is this way. But that would add a second dimension into the problem, and this is only supposed to be a one-dimensional problem. So when they say the wall, they mean back up the stick towards 0. Then let's see, 3 centimeters toward the floor. This is a really indecisive bug. And by that time, it's all tired out, so it takes a rest. Then it goes 25 centimeters more toward the floor. Then 19 centimeters back towards 0. Okay, so what we want to do is find the total displacement and the final resting place on the stick. So the bug's been wandering all over the place. Find out where it ended up. You want the total displacement at the end of the bug's wandering and its final resting place in terms of the numbers on the measuring stick. So I'll say the final location in terms of the numbers on the stick. Okay, so for the solution, first thing we'd want to do is actually what we already did right here, is define the directions, if assuming you haven't done it already. Okay, positive unit vector for the direction will be toward the floor, and the negative direction, or the negative unit vector, will be toward the wall or away from the floor. All right, so that helps. And it always, actually, in questions like this, even fairly simple ones like this, it almost always helps to draw a diagram. So that's something you should definitely get in the habit of. Draw a little picture or a diagram of what you're working on. In most cases, it doesn't have to be super accurate in terms of magnitudes or angles, but try to get it as close as you reasonably can. And certainly magnitudes should be at least relatively in the ballpark. If it says vector A is twice as long as vector B, then try to draw it with vector A being at least approximately twice as long as vector B. But they don't have, for most cases, they don't have to be exactly proportional. In most cases, you're drawing a diagram just to sort of get a better idea of what's going on and how things relate to each other. Okay, so what we have to do now is you want to define each segment of movement in terms of displacement. We can designate them, let's designate them like segments 1 through 5. So the vector for displacement in the first bit of movement was, the problem says, the bug lands on 100 and goes 15 centimeters toward the floor. Toward the floor is a positive direction, so we're going to call this 15 centimeters times the positive unit vector. Of course, when it's positive, you don't have to actually write plus to convey that. Then it goes 15 centimeters away from the floor, or toward the 0 centimeter mark on the stick, and that would be the negative direction as we've defined it. So the distance is still positive. The magnitude of the vector is still positive, but it's the vector itself that's negative, because negative, again, denotes direction. Okay, the third segment, it says then 3 centimeters toward the floor. That's going to be 3 centimeters times the unit vector. Then it takes a rest. Then 25 centimeters more toward the floor. So that's 25 centimeters times the unit vector. Then 19 centimeters back up the stick away from the floor toward the 0 centimeter mark. So that's D5. The final displacement will be the resultant. And so our final displacement would be just the sum of all of the displacements that we have so far. Notice I haven't subtracted anything, even though some of them are negative. We're just dealing with the names of the vectors right here. So you just add them up and worry, when you put in the values, we'll worry about which ones are positive and which are negative. Okay, so this is going to be D1 is 15 centimeters times the unit vector. D2 is 56 centimeters times the negative unit vector. And then D3 is 3 centimeters times the unit vector. D4 is, 25 centimeters times the unit vector. And then D5 is 19 centimeters times the negative unit vector. And what we can do is gather together all of these scalars along with the negative signs from the vectors, and then multiply them just by the unit vector. So another way of saying this is 15 minus 56 plus 3 plus 25 minus 19 centimeters times the unit vector. And altogether, that gives you negative 32 centimeters times the unit vector. And that would be your total displacement at the end of all the wanderings. And what that also means is that the bug is 32 centimeters above, higher, that is, toward the zero. So in other words, it's 32 centimeters away from the floor, because that's the negative direction. Going down toward the floor was positive. So if it's negative, it's going up the stick away from the floor. And but that's relative to where it began. Where it began was the 100-centimeter spot. And it's 32 centimeters toward the zero from that. And so 100 minus 32 would be 68 centimeters. That's where the bug ends up. All right. Oh, that's fun. Okay, you can stop the video and review that if you need to. It's yeah, again, it's still one-dimensional, so it's not that complicated, even though there was a lot of back and forth in this one. There's another one down below where they don't work it out for you, so I thought I'd go over that one too. This one is a cave diver. Cave diver enters a cave when the displacement with respect to the opening of the cave, or the entrance of the cave, is 20 meters, she drops her camera. She proceeds 6 miles farther into the cave, and then she turns around to find the camera. She goes 10 meters back, toward the entrance. And what is her displacement at that point? Okay, so in the solution, we have, we can draw a little picture here, say, here's my very artistically drawn entrance to the underwater cave. And the diver is basically, oh, actually, the problem also tells you to define the positive direction as towards the entrance. Okay, so we have that. And essentially, the diver goes 20 meters into the cave. And that's where she drops her camera. But then she continues on 6 meters more before turning around and going 10 meters back. And so, the question is, what is the displacement vector at this point here? I'll call it point F for final. And also, did it ask that? It didn't ask, but we could also ask, what is her distance from the entrance? Well, we're going to find out her distance from the entrance as part of the displacement because we're measuring the displacement from the entrance. So she has essentially 3 segments to her movement. D1 is 20 meters in the negative direction because she's heading into the cave away from the entrance. D2 is going to be 6 meters also in the negative direction because she's heading further into the cave. And then D3 is 10 meters, and that's in the positive direction because she's headed back out of the cave at that point. And then the vector at which she ends up, that is the final location, is equal to just D1 plus D2 plus D3. And that's going to be 20 meters times negative u, the unit vector, plus 6 meters, also times negative unit vector, plus 10 meters times positive u, or unit vector. And so that's going to be equal to bringing all the terms, the scalar terms together, minus 20, minus 6, or plus negative 6, plus 10 meters times unit vector. Or in other words, negative 16 meters times the unit vector. So that is the vector of her displacement at the final point, and negative 16 just implies that she's 16 meters inside the cave at that last moment, which again is fairly simple to see from laying it out in a sketch like this. But like I said, there will be 2- and 3-dimensional problems in the future that'll be sort of harder to envision like that, so you need to be able to do the math. Okay, we're just about up to 25 minutes now, so the next topic is 2-dimensional vectors, but I guess I'll leave that for the next segment.